Hi everyone, I am Wijewardhana. Today I am covering Linux Energy Aware Scheduling, or simply known as EAS, part of the topic Modern CPU Architectures and Core Types for Parallel Computing module. Modern chips increasingly use mixed core designs, pairing small, efficient cores with large, high-performance cores on the same chip. EAS is the part of the Linux scheduler that decides which of these cores runs a given task, weighing both speed and energy costs together rather than speed alone. A traditional scheduler asks one question: which CPU can finish this task fastest? EAS changes that question entirely. It asks which CPU can run this task efficiently while minimizing the total energy consumed by the whole system, not just this one task. That's genuinely a different optimization goal. And the rest of this video is really just explaining how Linux answers that second question in practice. Let's make this concrete before going technical. Imagine two workers asked to move the same 10 boxes. Worker A, the big CPU, is very strong and finishes in 5 minutes, but burns a lot of energy. Worker B, the little CPU, is slower, taking 10 minutes, but uses far less total energy for the same job. Neither is objectively better. It depends on whether you need the job done now or want to conserve the energy. EAS is the manager making this exact call automatically every time a task needs somewhere to run. This trade-off exists because modern CPUs are no longer built from identical cores. Little efficiency cores draw less power and offer low capacity, designed for background and light workloads, aimed at preserving battery. Big performance cores draw more power but deliver high capacity, designed for heavy 3D or interactive workloads, aimed at maximum throughput. EAS exists specifically to exploit this split between core types. Without it, there'd be no efficiency designed to make in the first place. Before going further, we need to separate two terms people often confuse: power and energy. Power is the rate energy is consumed at any instant, measured in watts. Energy is the total consumed over time, measured in joules. Energy equals power times time. Here's why that matters. CPU A draws 5 watts for 2 seconds, so it is 10 joules in total. CPU B draws only 2 watts, which sounds better but takes 6 seconds, which is 12 joules. So CPU B used less power at any moment but consumed more total energy simply because it took longer. This is why EAS optimizes for total joules, not just low instantaneous power. So how does Linux know the energy cost of a CPU placement? Through the energy model, registered per performance domain, a cluster of CPUs that scale voltage and frequency together. Each domain has a lookup table of performance states. In our simplified example, low state offers capacity 170 for 50 mW, medium 341 for 150, high 512 for 300. This table is exactly what EAS checks before estimating the energy cost of any placement. EAS also needs to know how busy each CPU currently is. CPU capacity is the maximum work a core can handle, normalized on a scale up to 1024 relatively to the fastest CPU. Utilization, tracked via PELT, per entity load tracking, measures how much of that capacity is in use. Capacity minus utilization gives spare capacity, the headroom left. CPU A, capacity 100, utilization 40, has 60 spare. CPU B, same capacity, utilization 80, has only 20 spare, clearly less room for new work. Now let's put these pieces together into the actual EAS decision pipeline. A task wakes up and needs scheduling. Its utilization is measured using PELT. EAS then searches for candidate CPUs, specifically within each performance domain, the one with the highest spare capacity, to avoid triggering an unnecessary frequency increase. Using the energy model, it calls a function called compute energy to simulate total system-wide energy for each candidate. Finally, EAS compares those simulated results and selects whichever placement is predicted to consume the least total energy. Let's see this pipeline in action. A new task requires 20 units of capacity. Little CPU A has 50 minutes spare, and running the task there costs an estimated 10 joules while staying at a low performance state. Big CPU B has 80 units spare and would run the task faster but cost 20 joules, double the energy. EAS selects little CPU A. More spare capacity on the big core didn't decide the outcome. Lower total energy did. Now, here's an important notice. Little cores don't always win. All CPUs in one performance domain share the same frequency, since they scale voltage and frequency together. So imagine both little cores are already heavily loaded, say 90 and 85%. Adding one more task can force the whole domain up to its maximum performance state, raising the energy cost of every task already running there, not just a new one. Placing the task on a single big core instead costs more individually but lets the little domain stay at minimum frequency. In some cases, that save domain-wide energy outweighs the extra cost of the big core, which is why big cores can sometimes be the more energy-efficient choice system-wide. This exact scenario is worked out with the real numbers in the Linux kernel's own documentation. Task P needs 200 units of utilization. The little domain has CPU 0 at 400 utilization and CPU 1 at 100. CPU 1 with far more spare capacity becomes its candidate. The big domain has CPU 2 at 600 and CPU 3 at 300. CPU 3 becomes its candidate. At this point, EAS has narrowed the decision to two real candidates, CPU 1 and CPU 3, plus the option of simply leaving the task where it currently is. EAS now runs the energy model against each option. CPU 1 costs an estimated 1,364 energy units. CPU 3 costs 1,485. Staying on CPU 0 to cost 1,437. CPU 1 is clearly lowest by over 100 units of either way, so EAS assigned task P there. Not because it's the little core and not because it's fastest, but because the energy model calculates the lowest total system energy for the placement. One more safety mechanism rounds this out. Under normal conditions, system-wide utilization below roughly 80%, EAS stays fully active, continuously optimizing for minimum energy. Once utilization crosses that 80% threshold, the system is considered overutilized and EAS automatically disables itself for that part of the system. Control falls back to the standard performance first CFS load balancer, ensuring the system never sacrifices responsiveness just to chase energy savings under heavy load. Finally, EAS doesn't run on every Linux system by default. A few conditions need to be met. The hardware needs an asymmetric, heterogeneous topology, like big.LITTLE or dynamic IQ. An energy model with real power cost data must be registered with the kernel. Accurate PALT utilization signals need to be active. The system needs to be scheduled with CPU frequency governor, since EAS's predictions assume the governor's behavior, and in its standard form, EAS is designed for non-SMT configurations to keep its energy estimates accurate. So, to bring it all together, energy-aware scheduling is a shift in how Linux thinks about scheduling, from asking which CPU is fastest to asking which CPU gets the job done using the least total energy without sacrificing needed performance. So that's about EAS, Linux energy-aware scheduling. So if this helped you understand EAS, feel free to drop a comment. Thanks for watching and I'll see you in the next one.